Hello, I'm Sam Johnston and I'm an undergrad third year student of Biomedical Engineering.
My name is Robert Johnston. I am a PhD researcher here in Mechanical and Manufacturing Engineering. My PhD is mainly in the field of Biomedical Engineering.
I'm Kieran Sims. I'm an Associate Professor in Biomechanics at Engineering, Trinity College, Dublin.
I'm David Taylor. I work here in the Mechanical Engineering Department and also in the Trinity Centre for Bioengineering.
I chose Biomedical Engineering because I've always had an interest in biology and the human anatomy.
My background actually comes from physics, specialised in medical physics, and I also completed a Master's in Biomedical Engineering.
My research interest is in injury biomechanics, that is, how people get injured when they get hit, the mechanics of the tissues that get injured, and in the development of devices to prevent injuries.
My interest is in materials, in the way that materials fail and how we can try and stop them from failing.
The reason why I actually got involved in biomedical engineering is that I chose to do biomedical engineering in my Master's because it was a way for me to actually use all the skills and mathematical concepts that I learned in physics and apply it into the field of biomedical engineering.
Trying to apply Newtonian mechanics to the human body, which I haven't done at all through any of my modules at the time because there were none, and I really haven't looked back from that.
Studying bone and cartilage and all these materials that we have in our bodies, and indeed materials in the bodies of other animals and plants, all these living materials which they kind of make up for the fact that they're really not very good compared to metals and plastics and things that we make. They're not that good, but by being alive they can compensate for that. They can repair themselves and remodel themselves. I find that very exciting because it means I have to use my engineering knowledge, but I have to work with biologists and doctors and people who can understand the biological side of the problem as well.
You're taking stuff from computer engineering, maths and mechanics as well.
What I enjoy the most is that every day is different. As engineers, we always try to find, first of all, problems and then solutions to them problems.
Engineering, I think, is about the application of scientific principles to the development of new equipment or processes.
I think for anyone who is interested in science, who's interested in physics and biology, who wants to, particularly I suppose if you're interested in physics and maths and so you like doing that kind of work, well, here's a way of applying physics and using mathematics to do something that's really important, really practical in the world and can really help other people.
The most interesting part is definitely the biomedical based modules, anatomy and physiology, where you learn about the entire human physiology, all the intricacies of the cells and the organs, and then the biomedical design project where you take that understanding along with everything you've learned over the past 2 years and get to actually design a device that may go into production at the end of it. Along with that, you get to learn how to use a 3D printer, which is really cool.
My current research is actually a combination of MRI and computational mechanics to create real patient-specific 3D geometries. The disease that I'm particularly focused on is atherosclerosis and the development of plaque within the arterial wall. So the idea is actually to create 3D models of atherosclerotic arteries and determine where high stresses, high strains are and locations at risk of rupture.
The experimental projects relating to pedestrian collisions and our work on head injuries in sport, in particular in rugby. We have developed a method of analysing videos and doing computational models and experimental tests with instrumented athletes. That's helped us to understand how tackle height influences head kinematics and loading. We worked together with Leinster Rugby and colleagues at Trinity, and we did a combination of video analysis study. How did the players come together? What was the tackle configuration? And from that we started to look at computer models based on Newtonian mechanics to simulate these collisions. What if the tackle was lower? What if one player was heavier than another? And then we also set up lab-based tests with athletes where we put them in a motion capture environment and got them tackling each other and tried to see how well our computer models could predict what was going on in the lab. And we're also working with the Irish Road Safety Authority on a PhD study to look at the range of cyclist collisions in Ireland.
One of the examples of how engineers have made a big difference in medicine are these joint implants, the so-called artificial hips and artificial knees and all of these. And I've got some of these products here. For example, this is an artificial hip implant. This part goes into the person's pelvis, this part goes into the top of the femur bone, and it substitutes for that so-called ball and socket joint. These joints often break down in our bodies because of arthritis and other problems, and it's been a really successful operation over a number of decades now, where engineers working with doctors have managed to find ways of replacing that joint. So people who in the past would have had terrible pain and would have been unable to walk, now we can give them a new implant which will last for 10 years, 20 years and work really well. Sometimes they bring out new ones which don't work very well, so then I work to try and understand what's gone wrong and to improve things for the future.
The difference with biomedical engineering compared to medicine would be we can really change the way everyone in a hospital operates with the devices that we design. You're applying so much more understanding to these devices.
As biomedical engineers, we're trying to solve a problem for a wide range of people. Medical practitioners, when a patient comes in, that specific person they're actually designed to care for. Biomedical engineers, we design products and develop products so they can actually help the well-being of anyone. So for example, you might need a specific stent designed or a specific implant designed, and engineers, we can tailor that, something a physician or a medicine student cannot do.
I think people who understand science but for whom just the science is not really enough, people who want to make new things, who want to be inventors and designers, or want to improve things that they see in the world around them, or get involved in how things are made and try and make them better. People who can see their role as serving humanity through this medium of maths and physics that they're good at.
I guess there's some questions that you should ask yourself. Do you want to problem solve? Do you want to apply fundamental science to changing some piece of equipment or a process or understanding something that's happening in the world around you? Do you want to develop new equipment, new processes? Can you ask yourself, could this be done better?
If they like problem solving and working in groups of people, along with the ability to help people on a much grander scale than just working in a hospital where you're one-on-one with people most of the time, our devices can change everything.
It's very specific to people. That's what makes it very different to other engineering fields. People who have an imagination, have the ability to come up with these solutions to very difficult problems.
You don't have to be an expert in biology, you don't have to go in and be a brain surgeon and do an operation, but I think the kind of person who's good at this is someone who's open to new ideas and who's willing to communicate with people, with other people who have expertise in other areas.
Somebody who has strong capacity to understand fundamental science, but also the wish to apply it to change things in the world around them. And so they have to have an eye to how things are done at the moment, how they might be done better, and also to how they can develop the fundamental language of mathematics and science that will allow them to make evidence-based improvements. But they also need to be really creative.
A good engineering student has to be good at problem solving. That's the main thing with engineering. You have to be able to work in a team. You're working in a group with projects and lab reports all the time. You have to be able to apply principles from every single module you learn through the years in every single part of the course.
When I look at these implants, for example, and try and work out in some cases what's going wrong with them and then advise the companies on how to make them better, the feedback there is pretty quick. Within days or weeks, you feel that you've actually achieved something, and so that's very satisfying. It gets me into work every day anyway.
You don't have to actually necessarily have an engineering background to contribute into the field. You can come from, say, a chemistry background, biology background, or even a physics background.
Each individual engineer will have some combination of those strengths. Not everybody needs to be very strong on all of them, but collectively as engineers, that's what we try to achieve.